everyone. Thank you for attending this presentation today. Let us start right away with the goals of this presentation. So first of all, I would like to present a part of my previous work during my PhD thesis. Secondly, I will try to identify the areas related to security in this team. And finally, I hope that I will be able to bridge my previous work during my thesis with some areas of the research that is going on in the team. This talk is partitioned into two main parts. So in the first part, I will present two of my main protocols which have been proposed during my thesis. And in the second part, I will, and I expect more interaction with you in the second part, where we will discuss a little bit what is happening in the team, and maybe we can come out with some ideas to bridge my previous research with the current research in the team. First of all, I will start with the first part, and I will start with these startling numbers, impressive numbers. In 2020, we expect 4 billion people to be connected. We expect more than $4 trillion of revenue opportunity, more than 25 billion of embedded systems and objects connected together. These impressive numbers are the potential impact of the Internet of Things. So one might say, what is this technology? Internet of Things is basically a technology that allows the objects that we can find in our everyday lives to gather data, transmit this data, store data, and also process it. So this interconnection will open the door to a huge number of possible applications. So we might find applications ranging from transportation to smart energy, passing with healthcare and several other domains. To deploy the Internet of Things, several architectures have been proposed in the literature, but a high-level architecture is commonly accepted and presented in the state-of-the-art with three main layers. The first layer, we find the devices that are able to gather data, so we can think of cameras, sensors, RFIDs, near-field communication devices, and so on. So the idea is to gather data and to transmit this data to the network layer, where this data will be processed and transmitted to the application layer, where it can be used in various applications. During my thesis, I focused an important part of my work into the IoT architectures and protocols. How are we going to deploy this technology? And we proposed a classification of these architectures. In the first class, we gathered the architectures that we called tailored architectures. These architectures and protocols existed before the Internet of Things and have been used for a long period of time within the classical Internet. The idea was to take these protocols and to adapt them to IoT specificities. This is good because we ensure backward secrecy, backward compatibility doing so. But unfortunately, by modifying existing protocols and tweaking them, we can create some bridges, and more importantly, some bridges related to security. The second class of protocols is called the clean slate architectures and protocols. These latter have been designed from scratch, taking into account IoT specificities. So this is good because during design time, we can take into account the characteristic of the technology, but unfortunately in this category we can find several problems of compatibility, of backward compatibility with existing protocols. As a result of my research on these architectures and protocols, we come up with the conclusion that it is important to design architectures and protocols for the Internet of Things instead of letting the current protocols raise in an uncontrolled way. These architectures are not contradictory, so we can imagine hybrid architectures with several approaches that can intervene in a particular layer of the network. I invite you to take a look at a book chapter which have been published in a Springer series of system decision and control, you are going to have more details and more insight on these aspects related to architectures and protocols for the deployment of IoT. Now, I will go through some concepts related to security. Before diving into details of the proposed protocols, I would like to shed some light on some basic concepts related to security. A lot of people and sometimes researchers confuse between two main concepts, which are security and privacy. Privacy is more related to users, whereas security is related to data. So a system can be secure, but not privacy preserving. Actually, privacy is related to users, where we can think about a user that share its information in a particular context, and later find out that this information has been shared in completely different contexts, shared or sold, actually. And security, on the other hand, is more related to ensuring a set of properties. We can think of an important property, which is access control. Basically, in this case, we make sure that only authorized and genuine people can access to some resources. Generally, we pass through three main steps. The first one is identifying users involved in the system. Secondly, we make sure that these identities are genuine. This is the authentication property. And finally, we set the authorization for these users regarding each resource. A second important property is integrity. This is to make sure that when data is transmitted between two users, this latter has not been modified during the transmission. Another important property is non-repudiation. This is to make sure that a user cannot deny performing an action in the system. And we also have data confidentiality. This is to make sure that data is only accessed by the users that are part of the exchange. How generally we ensure this property? Generally we use cryptography. And based on Kirchhoff principles, in any cryptographic system, the algorithm used to encrypt data is public, and the keys are secret, and not the other way. So these keys need to be generated, transmitted, managed, and this is the job of key management protocols. And this is the main focus of my work during my thesis. One can say, what is the problem with the current key management protocols? A lot of them exist in state of the art and have done their job well during previous year. Unfortunately, we cannot take these protocols and apply them to the Internet of Things directly. This is due to several reasons. First of all, the devices employed in the Internet of Things will be very limited in both power and computational capabilities. In addition, the heterogeneity of the devices is also very important. So let's imagine a tiny device planted in a human body with very limited resources take part into an exchange with a remote server in a TLS negotiation, for instance. This will definitely generate some problems in the end-to-end communications. And finally, there's also the scalability issue, as we're going to have a huge number of devices taking part into communications in the Internet of Things. In my thesis, we proposed several protocols that we gathered into two categories. The first one is the centralized protocols. In this part, the protocols are based on a central entity that is in charge of generating the key, distributing it, and maintaining it. In this category, we proposed an interesting approach on the Mickey ticket protocol. Mickey, it's not Mickey Mouse, but it stands for Multimedia Internet Keying Protocol. In this part, we proposed an adaptation of this protocol to the context of IoT. So what we did is that we reduced the number of exchanged messages by proposing a new mode exchange, and we also reduced the size of the header that is appended in each exchanged message. I invite you to take a look at a journal paper which has been published a few days ago in the International Journal of Sensor Networks. We're going to have much more details on this part. But today, I will move more focus on the second category of protocols, which I think are more related to collaborative editing and collaborative applications. So I will go into the first protocol briefly, but I will take more time during the second protocol because this protocol is more related to group communications, and I think that it concerns the team much more. Let us start with the first protocol, which is entitled an end-to-end secure key management protocol for IoT applications. So what are our motivations for this protocol? Basically, the idea is to make sure that a smart object can exchange. When I say smart object, is any device, any tiny device that is able to gather data, process data, and communicate data. This is what I mean by smart object. So the goal is to make sure that this object is able to establish a shared secret with any remote device without previously having shared any secret. And in addition, we want to make sure that we ensure the end-to-end principle, which means that no other entity, apart from the two taking part in the exchange, is able to retrieve this secret. And obviously, we want to ensure both these properties with very limited communication and computational overhead. What has been done in the literature regarding this aspect? Several protocols have been based on the idea of delegation. So basically, we delegate the heavy computational operations to a third party, and doing so, we spare the device from being part in heavy computations. But unfortunately, we noticed that in general, these approaches break the end-to-end principle. What does it mean? It means that in these cases, generally there is another entity that is able to retrieve the secret. In some sensitive applications, this is really not a good idea. For instance, if you have applications, we definitely don't want to have our data be accessed by a third party apart from the remote entity with which we want to exchange data. So to deal with this issue, we propose our protocol with the aim to merge between symmetric encryption and asymmetric encryption. The idea is that asymmetric cryptography has a lot of advantages. Most importantly, it allows us to establish a secret with a remote entity without having previously shared any secret. Unfortunately, this kind of cryptography is very energy consuming and is definitely not adapted to devices with a lot of energy and computational constraints. In this figure, I will give you a broad idea about the protocol. So the goal is to make sure that a tiny device planted, in this case, we take e-health scenario, so we can imagine tiny device planted in human body, inside human body, or around human body. So the idea is to allow this device establishing the secret with a remote server. Using asymmetric cryptography, this is straightforward. But what we wanted to do is to spare the device from being engaged in asymmetric cryptography. So what we did, we relied on a set of third parties dedicated to assist this constrained device in its operation of establishing a secret. So our network architecture is divided into two main parts. In the first part, communications are secured using symmetric encryption between the device and the third parties. And in the second part, communications are secured using asymmetric encryption. So the basic idea is that the device generates a key, so provide a very general overview. The device generates a key. This key is a secret, not the final key, but a secret that is split into several parts. Each part is encrypted and secured with the shared key that is established between the device and the third party. After receiving the message, each third party will authenticate, decrypt the message, and then re-encrypt it using classical public key infrastructure with the remote server. What we need to understand is that the remote server, we assume that this server is not constrained in resources and both computational and energy. So public key encryption will definitely be possible. And after receiving all the parts, all the shares of the secret, the remote server can then reassemble the secret. What we need to understand is that in the state of the art, there are a lot of functions that allow such a split of secret. And what is the main advantage of this approach is that unless all the third parties collide together, there is no way for one or two of them to retrieve this secret. So it is clear that the more we have third parties, the more the system will be secure. But the energy evaluation that we made showed that the more third parties we have, the more message will be exchanged, and unfortunately the more energy overhead will be important on the device. So we may want to find kind of a trade-off between security and energy overhead in this kind of architectures. Once again, I invite you to take a look at the paper that we published regarding this approach to have more details, and obviously we can discuss it after the presentation. Now we move to the second protocol. So this approach, and even the first one, allows us to establish secrets between two different entities. But it is clear that in the Internet of Things, we're going to have several applications that will be based on group communications. To secure these communications, obviously, we're going to need group key management protocols to managing these groups. And the challenge is that IoT presents several properties that are specific to this technology and that we don't find in other technologies or in the classical internet. First of all, we're going to have large groups of members with unpredicted member joining, member leave, also events. We're going to have members that will be part of the group for a long period of time without being necessarily active. So we have to take this aspect into account. We're going to have mobility issue, members will be very dynamic, and of course, limitations in resources. I'm just going to start with, I'm going to take a few minutes to talk about what has been done in the state of the art. Group key management protocols are generally classified into two main categories, centralized categories and distributed categories. In the first one, we're going to find central entity, so obviously we have a single point of failure here, but we have the advantage that these protocols are very simple and does not require asymmetric operations. In the distributed category, there's no central entity, full peer-to-peer communications, but these protocols are generally based on a distributed version of Diffie-Hellman, and Diffie-Hellman is mainly based on exponentiation operations which are very expensive in research, in resource consumption. So this is basically the main advantages and disadvantages of these two categories. We can add a third category to more refine this classification, which is a decentralized category. In this part, we're going to have protocols that are based on central entity, but which is decentralized, which means that we have several decentralized, several central entities. And in this case, we're going to have two other subcategories. We can find a common traffic encryption key for all the group, or several independent traffic encryption keys for each subgroup. Our proposed protocol is categorized in the decentralized category. One of these protocols attracted our attention is the protocol published in 5 by Viltri and al. I will give you a broad idea on this protocol because our approach is based on the improvement, is based on the gaps that we spotted in this approach. So we spotted several gaps, and what we did basically is that we proposed an enhanced version of this protocol. This is a time-driven protocol, which means that the time axis is split into several intervals, and for each interval we have a different group key. The group key is computed as the combination, f is a one-way function, so the group key is a combination between a long-term key, k, which is shared among all the members of the group, and short-term key, which changes at the end of each time interval. So the basic idea is that they base their protocol on the fact that we can sometimes predict the duration during which a member will be part of the group. So if a new member wants to join the group, the member will just say, I want to be part of the group during 10 time slots, for instance. Doing so, the central entity, or we can have several central entities, can distribute exactly the amount of keying materials corresponding to the time during which this member will be part of the group. What we have to keep in mind is that the most important challenge in group key management is that every time a member wants to join the group or leave the group, we need to change the key for everyone. Because if a member joins the group, we don't want this member to have access to previous communications. And if a member leaves the group, we don't want this member to have access to the communications that will take place after its leave. More importantly, a member can be ejected from the group, so we don't want this member to have access. So changing the key every time, in particular in dynamic groups, is really challenging. And all these protocols aims to reduce the impact of this rekeying that happens every time. Let's go back to this protocol. So the idea is to distribute the corresponding number of keys during which the member is part of the group. And obviously, if a member will be part of the group during a long period of time, this member will receive a huge number of keys. So this is why they came up with a trick or an idea to reduce the amount of keys distributed. So I'm not going into the details of this approach. Basically, they proposed a tree to reduce the complexity from O(n) to O log n. So this is basically what they proposed here. In this protocol, we spotted several drawbacks. First of all, even though they proposed this trick to reduce the complexity, still, if a member wants to stay a long period of time in the group, this member will receive a long message with several keys. So if the devices employed are limited in storage capabilities, this would be obviously a problem. Another problem is that the protocol is based on the fact that we can predict the duration during which this member will be part of the group. Unfortunately, if the member leaves the group in an unplanned way, if we have leave that was not expected, obviously we're going to change the key for everyone using LKH. LKH is the state-of-the-art protocol to rekey group key systems, which this protocol have a complexity of log n. But obviously, if we have frequent unplanned leaves, we're gonna fall back to the LKH situation. And also, all the members of the group will have to compute the group key at the end of each interval, because the short-term key changes every time. So if a member wants to be in a sleep mode, for instance, in sensor networks, when a node is not active, it can be put into sleep mode to save energy. So this case is not possible here, because at the end of each interval, the node has to recompute the key every time. So introducing time intervals in LKH is interesting. However, this is not adapted to very dynamic situation with frequent unplanned events, and with also the case where members can be part of the group for a long period of time without necessarily being active. So this is why we proposed our protocol with these features. First of all, our approach is not based on the prediction of the departure of the member. This is obvious, because in IoT and in any other dynamic systems, we're not going to be able to predict this kind of things. Secondly, only the active members will be employed in the rekeying process. So if a member is not active, this member will just not be bothered with the rekeying at the end of each interval. And also, during the joining process, each new member will receive only the long-term key, and after that, if the member is not active, it will just not receive any key. But if it wants to be active, it will ask only for the keys corresponding to this particular action and not corresponding to all its presence in the group. And also, we have a part related to mobility, but I will not go into details regarding this aspect. This is the general architecture of our protocol. So we base this protocol based on decentralized central entity. So we have a general key management server that manage several other area key management servers. So the group is divided into several subgroups. Members can join and leave any subgroup in an unpredicted way, and members can move from subgroup to another one. Here I will talk very briefly on two cases. So protocol basically reacts to event. So as soon as we have an event, there is an action behind to respond to this event. For instance, this event is related to the joining of a new member. So this member will basically send a join request to the area key management server, which is forwarded to the general key management server that makes the final decision based on authentication parameters. And most importantly, I want to focus on the leave event. This is the most important part. In this part, we consider two different situations. In the first one, the leaving member has not in its possession any short key. So in this case, there is no rekeying required. Why? Because this member will not be able to retrieve any key after its departure. So in this case, we have zero operation required. However, in the case presented in this slide, we assume that the key lives in the group with in its possession one or several short keys, which I call tickets in my case. In this situation, what we need to do basically is to notify all the members that had the same tickets or short keys that those possessed by the leaving member, to say your tickets are no longer valid. So this letter will need to ask for other tickets. In the evaluation part, we will see the impact of this kind of operation. So I will skip the other events. We can discuss them after the presentation. And I will skip to the evaluation part. So how did we evaluate this protocol? We focused on two main aspects. The first one is related to security. We did analytical analysis validated by a formal validation using, we used two tools actually. The first one called Avispa, the second one called Skyter. And the energy part related to energy estimation. So in this case, I will only talk about the energy evaluation. And this is the complexity resulting of each event. So what I propose is that we discuss these results on the figures that shows the evaluation of energy consumption. I think it's clearer than talking about complexity. So our simulation was performed using CODA, which is a simulator of the operating system Contiki. We used the CC2420 encryption to simulate hardware encryption to secure the exchange messages. And to measure energy consumption, we used PowerTrace, which is a tool that allows estimating the time during which a member is in active state, and then we can compute the energy consumption. So here I will focus on two main results. The first one is related to the joining event. As we can see, we compared actually our protocol with several other protocols which are the state of the art regarding group key management. So we can easily notice that LKH, the energy consumption of LKH increases significantly compared to other protocols. This is due to the fact that LKH is the event-driven protocol, so after each event, this protocol will react. So several messages are exchanged during the joining event, and this is why the energy consumption is high. But regarding other protocols, we noticed that DBGK, which is the protocol we proposed, its energy consumption is steady and does not change with the variation of the number of nodes. This is because at the joining moment, we only send one message with a long-term key, no other keys. The other keys are sent every time the member will be active. And here I will talk a little bit about the leaving event. I think this is the most important result of our protocol. We compared our protocol with LKH and Viltri. This case is related to the case where a member leaves the group unexpectedly. What we did, we simulated the network of 1,000 nodes, and we variated the proportion of nodes that are in possession of the same ticket as the tickets in possession of the leaving member. So we can notice that up until approximately 50% of nodes with the same ticket, our protocol is less energy consuming compared to LKH and Viltri and our protocols. But after that, the energy consumption increases dramatically. So at this point here, at approximately 50%, what we did is that we switched it to the LKH protocol. So as a result, our protocol is, in the worst case, equal in energy consumption to the other protocols. This is a very important result of our approach, and obviously we can discuss this in more detail after the presentation. Now we'll move to the second part of the presentation. I expect more interaction with you in this part. So I selected two articles, two papers published by the team, and I will just give you what I got as a basic idea, and I will give some feedback. And if I'm wrong, you can intervene. The first paper is entitled "Log Auditing for Trust Assessment in Peer-to-Peer Collaboration" by Truong and al. So basically, the idea is here to enforce trust using the concept of contracts. So if a user respects the contracts established in this exchange, its trust level will raise, and in the other case, the trust will just decrease. And also, mechanism for managing the merging of logs in case of conflicts has also been proposed. In this case, I spotted some, not shortcomings, but maybe some extensions that we can think of. First of all, in the paper that I read, log tampering has not been taken into account, and in particular, users' collusion. For instance, if a user has a contract to respect, and in the contract, we can imagine that the user should not share a document, for instance. Imagine if I'm colliding with another user and I share this document with this user. If this user does not include the fact that I shared the document in the log, we will not be able to detect this misbehavior. So if users collide, it will be difficult to detect such misbehavior. I don't know if it has been done on purpose in the paper, but maybe we can talk about user collusion and the authentication of logs. How can we make sure that logs are not tampered in this system? This is one paper. And the second paper that I selected for today is a paper entitled "Enhancing Access Control with Risk Metrics for Collaboration on Social Cloud Platform." This is from Bushami and al. So it is clear that enhancing existing access control policies with contextual information is important, and this is what Bushami did. They enhanced existing access control policies with the concept of risk. And the risk is computed as the combination of vulnerability, threat, and impact. Honestly, I've been a little bit troubled with the way that they think about the concept of impact. Basically, what they said is that if a resource has denied a lot of attempts of access, this resource, accessing to this resource will have a high impact. I disagree a little bit because we can imagine that a resource can only be accessed by authenticated people, so we're not going high level of denied access, but at the same time, the impact of this resource can be really, really important. So maybe we can think about the way this concept has been think of in this paper, and also the fact that this is only this is only in addition to existing. I mean, we need classical access control mechanism upon which we can add this kind of risk context and so on. So I mean, even with this kind of approaches, we still need classical and hard access control mechanisms. So this is the two papers in the past research that are really related to security. The other papers that I read are more related to data replication, data consistency also. So I only chose these two papers. And now I will talk a little bit, I will say 2 words about current research related to security. Obviously, to secure any system, we need to make sure that the credentials are authenticated. And after that, we need to distribute this credential using key management protocols. And finally, we can use encryption or any other system. So now we'll talk a little bit about Long's research. I had the opportunity to discuss with Long, and he told me that he's working on the authentication of security credentials in distributed ways. So the basic idea is to avoid using central entity that will authenticate the credentials, but is more working on, and you can correct me if I'm wrong, is more working on distributed approaches, which are really close to Connex. I don't know if you heard about Connex, and blockchains also that allow authenticating credentials without central authority. There is also Victoria, who is working, unfortunately he's not here today. He told me that he's working on data consistency, but in a few weeks later he will work on, he's not really sure about the topics that he will work on. He told me maybe key management protocols, maybe credential authentication, so he's not sure. And so this is actually, there's Monk and Victoria who are really working on security. So I'm still looking for a direction that I can follow to contribute something to the team. Maybe we can think about peer-to-peer version of the protocol DBGK. For instance, this is only brainstorming, so I'm only saying things. We can think of the area key management server and general key management servers. These roles can be played by the members themselves, so we can think this kind of distributed solutions. So once again, I'm still thinking about future research directions, and I think that's all. So thank you for your attention, and I'm happy to answer any questions you might have. And these are the references you can access. Thank you. Any question?
Yeah. How do you differentiate between a leave and a sleep from a device, for instance? I mean, you mentioned that a device could go to sleep, but if we imagine it's not leaving the exchange, it's just sleeping, and then it could raise again. And so how do you ensure that the keys you will receive, and it's different, but a group, in a sense, a human group. So how?
This is a good question. Actually, there are several mechanisms to ensure sleep mode in sensor nodes. When I say sleep, it doesn't mean that the sensor is not active at all. It's just that the sensor is not in listening mode. Because if the sensor is in the listening mode, it will consume a lot of energy. So in sleep mode, the sensor can periodically sense send short messages to the area key management server to say, okay, I'm still here. So sleep doesn't mean that the sensor is not active at all, but it means that it reduces drastically its activity in the group. So there are mechanisms to make sure that the sensor is still in the vicinity of the group.
About what you mentioned in the work of Hien, the paper of Hien, Trong?
No.
Yeah, Trong.
Trong.
Hien Trong.
Trong.
Yeah. So here you said log tempering.
Yes.
I don't know if you have seen, but we have worked on that. It is not in that paper, maybe. I don't know which. It's the paper that has this title.
Yes.
So it's we didn't describe there the log tempering, but it's described in her thesis and in the paper that is at Group 2012. So basically, we worked on group tempering. So we detect if a user is trying to change the log. So we work with signatures, and then we use hash chain mechanisms that are based on Merkle tree and so on. And we detect if somebody changed the log.
Okay. But what if a member doesn't change the log, but just doesn't include something?
Yeah.
For instance, I share with you a document.
Yeah.
You are supposed to add in the log that I shared this document with you.
It is added.
But if you don't do it, how can we? There's only you that knows that I shared the document with you. So if you don't add this line in the log saying Riyadh shared the document and he was not supposed to do it.
But in that case, you have to modify the application instead.
You
have to modify the application to share the log without to share the document without logging, and that is impossible.
Yeah. So anyway, when you share the document with me,
Yes.
somehow I see that
That's what you
you
are
share.
uploading. You are
So anyway, it is put it in the log, and somehow it's also detected when you when you
who puts
exchange.
it in the log?
The
Based on the
system,
paper, it's the
it's also-
receiving user that is supposed to add this in the log. If I send a document to Long, he's supposed to say, I received a document from Riyadh. And another user can say, oh, Riyadh was not supposed to share the document. Why did he do it? And then the trust will be reduced. But if Long, I'm colliding with Long, he's not genuine, he's misbehaving, and he will not add it. So he has access to the document, but he will not say, I have access to the document. So basically, this is a case where users can
But when
collide.
he's taking your information from you,
I share the document
Yes.
with him.
yes,
Yes.
it is put it in the log you have.
Yes.
You put in the log
But
that you share with him.
I'm not.
I mean, the
in
system is
contract,
adding.
in the contract, it is said that I doesn't have the right to share the document. So I don't want the other users to be aware of the fact that I shared the document. So I will not put it in the log. And the log. And Long will also not put it in the log. In this case, when two users collide,
But somehow we
maybe we
detect
will-
from the system also that there is an exchange.
Yeah,
You
but-
share the data
Our
with
work is that if you are able to modify the system, then you are able to.
Yeah,
And
yeah, okay.
I think the only solution is to have a trusted platform.
Yeah, so if you go to the
And anyway, I think the base assumption is that you cannot tamper the applications. And anyway, like there's no way you can prevent people to take a screenshot and,
yeah, you know,
and
it's,
give to others.
you know, even if you don't share the document, you can take a photo
Yeah.
and then give to somebody else through another channel. And this I cannot control.
yes, true.
So if attacks are at the level of the system, we cannot detect them. So we
Yes.
didn't work on
And
that.
anyway, like if you want to tamper the applications, you can always put like a verification code for the system, like the hash of the whole system, to compare before you start chatting.
So once again, the log tampering, as you said, you worked on it on different paper.
Yeah.
But I was more concerned about if a user it's not that the user will not modify the log, but we just not insert things. But because the system is based on the fact that users insert everything every time an action is taken.
Yeah, but we
It
assume
has to be.
we assume that when you exchange the data with him, I mean the application will know that you exchange, because you do a commit and the other is doing a pull, you know.
Yes,
a push and pull.
I
Yeah.
missed this point.
Mm,
Okay, so basically I found this work of Trong and also of Bushnami that are really close to security, but the other papers that I found are more related to data replication, data consistency, how to make sure that data is.
Yeah, because it's somehow
Yes, this is why I
a
focused
newer
on this.
topic in the team.
This is why I focused on these two papers. And of course there is no Victoria or Ken.
For me, it was not very clear about your protocol DBGK. I mean, what was missing in the previous protocol? It was a bit faster, maybe.
Yes, because I didn't want to take
yeah,
a lot of time, so
yeah,
I just
but
tried
maybe
to-
it's because me I didn't get it, so that's good.
Yes, we can.
What is the difference between the old protocol you tried to adapt and what did you propose exactly? What is the changes?
The main
Can we
difference.
go back to
Okay,
the
of course.
slides?
What is reference number 5 mean?
Sorry.
You put,
Yeah, references sometimes a bit.
you put number 5 there, but I don't know what is number 5.
Number 5, this is the, okay, can go back. Okay. 5, this is the reference of number 5.
Does it have a name?
Yes, you can have a
No,
look.
I mean the name of the program.
There is no name, this is why I kept Veltri and
Or similar to Mark.
this protocol is not named. This is why I kept only the reference. I called it Veltri and all protocol. So maybe I will explain in the it's better. So
And you didn't have another paper on transactions of secure and dependable systems?
actually this paper is under review, still under review.
Okay.
Because this paper is an extension of this is a conference paper, and what we did is that in this paper we only included the energy evaluation. In the long version of the paper, we did some evaluation regarding the security part to make sure that to formally validate the protocol, and it's an extended version. It's not published yet.
About then the formalization, how was it very difficult, or how hard was it to use Avispa and validate the protocol?
Yes, to validate the protocol, we did two parts. So first of all, we analyzed each property, for instance, backward secrecy, forward secrecy, key dependence, and so on. So we discussed each property side, and then we used Avispa and Skyter, but in the paper we just highlighted the Avispa results. So what we did, we modelized the protocol. So you are going to define set of users and the different message exchanges between the users. And the Avispa proposes a language called HLPSL. Using this language, we can model the behavior of the protocol. And then we use an attacker model. Generally, they have default attacker model that can detect flows in the message exchanges regarding, for instance, particularly regarding data confidentiality and also authentication. So using
This
these
attacker
two-
model is in Avispa already?
Yes. Yes.
Okay, and you don't have specific attacks for your protocol that are not specified there?
Actually, they assume that their attacker model is really strong. They assume that the attacker is the network. I mean, if the attacker has the key, the attacker can modify data, so their attacker model, we don't have the possibility to modify it. So we need to rely on this model. And Skyter proposes the same attacker model with other models which are weaker. So in our case, we only focused on the attacker model existing in Avispa. And after modeling the protocol, we find out the protocol, the tool displayed an attack, which pushed us to modify a little bit, nothing big, but a little bit some parameters in the message exchanges. And we put down these results in extended version, and we submitted it as a journal paper. So this is why I put here only the conference.
So it was effective to use that too. It was, I mean,
Yes.
Not anymore.
hmm?
Not anymore.
Not anymore?
Like Skitter, like previously I used Skitter as well, but I found some bug in the tools.
Yes.
And the authors suggest that use this new tool instead. So you have to go to these new tools called Tamarin.
Yeah, Tamarin.
Tamarin.
Tamarin. So it's
Recently he has worked in Skitter, so
Okay, but
so we had to use new tools.
yes.
They use that also at TTH in the group of databasing.
ETH created.
Created that, yeah.
So if you want to go back to protocol 5, so what we did is that in our protocol we didn't think of the members as planned. We didn't think of a planned duration during which the member will stay in the group. In 5, a member will come and say, I want to stay 5 time slots. Okay. And the central entity will distribute the corresponding 5 keys.
So this is existing work. Now you try to explain me the difference
Yes,
between existing work and your
Your
DBGK.
Right, yes.
Okay.
In this work, what they say is that if you want to stay 20 time slots in our group, I will give you 20 keys.
Yes.
Doing so, at the end of these 20 time slots, when you leave, there is no need to change the group key.
Yes.
Okay. The problem is that if the node leaves before the end of these 20 time intervals, we have a problem.
Yes.
Because the node will be able to retrieve the group key in the remaining time intervals. So what they propose that in this case they will change the key. And this is not really adapted to the Internet of Things. So what we did, we proposed something different. When a node joins the group, we will only give him the long-term key, because a member can join the group but not be active immediately. Can join the group, be in the group. Let us think about e-health applications. We have sensors planted in the body. The sensor is part of the group, but it's not active all the time. The sensor will periodically transmit informations. Let us imagine a person affected with diabetes disease. At the end of each day, the sensor will transmit the value of sugar in the blood. So the sensor is not active all day long. So when the member joins the group, we will give him the long-term key. And after
What
that,
means long-term key? For how many periods?
the long-term key is not
Correct.
supposed to change. So the group key is the combination of 2 keys. This one is the long-term key, and this one changes at the end of each interval. So we only provide him with this one. And after that, if for instance, let us imagine that the member joins the group at this time, so we have time intervals, and then the member wants to be active during only this time interval. So we are going to provide him with this short-term key only. He doesn't have to store all the keys and maybe be active in 1, 2, or 3 time intervals. Doing so, when the member leaves the group, if it doesn't have in its possession these keys which I call tickets, there's no need to do any rekeying. This is the first case. In the second case, if this member leaves and it has in its possession a short-term key, this is a problem because it can access data after its departure. So in this case, and this is an important difference with 5, what we do is that we do not change the key for everyone, but we will say to the members that have this ticket, that your ticket is no longer valid. So you need to ask the central entity for new tickets. So only the members that are active will be involved. The other one that are part of the group but are not active will not be bothered with this problem. However, in 5, every time a member leaves the group unexpectedly, we change the key for everybody, even if a member is definitely not active.
So can you apply this idea to collaborative editing where you have peers that are online and offline? Can you apply this?
Yes, but the problem that I found is that in the team in general, I noticed that it's very important to avoid central entity. So the whole project is to say we believe in peer-to-peer communications. So I can say in the protocol that we have key management server and peers. It will not be.
But you can assume it is distributed.
Yes, this is what I want to do. The idea that I had is that we can think that the role of key management server will be played by members themselves. And not always the same member will play the role, but it will change. I don't know if you got the idea. Instead of having an area key management server and several members, we consider them as being all members, and for every...
Yeah, but when one is offline, you have the service that is not working.
Yes, we have to enforce mechanisms of, how can I say?
You need a replication.
Backup, yes. I don't know, maybe we can think of such idea. Because the only problem that I found in this protocol regarding its application on collaborative editing is this central servers. We cannot use it the way it is because obviously it's not compatible with what the team is doing. For instance, Long is trying to avoid all this central, and I think Victoria also will do the same thing. So I can propose something where I say, okay, we have key management server. Maybe I can
That is a key infrastructure, but just that it's distributed.
Yes.
But you just need there to ask for the key, for a new key, right?
Yes, but if this one is down, we're going to have problems. So we need to think about this. We have the, I don't know, we'll go back to very briefly to this network architecture.
So then why, if you compare with the Diffie-Hellman,
in this
distributed Diffie-Hellman solution, why,
yes,
why is it your solution better than?
it is better because the numbers are only applied in symmetric operation. There is no exponentiation because Diffie-Hellman is, I don't know if we go into details, generally there's a lot of exponentiations in Diffie-Hellman to retrieve the secret. And this operation is very energy consuming in small devices. We want to avoid these exponentiation operations. In asymmetric protocols in general, for instance, RSA also uses exponentiation. So we want to avoid this. This is what we try to do in the context of Internet of Things.
Yeah.
But Diffie-Hellman is obviously...
I was
better.
asking in the context of collaborative editing. Okay.
In the context of we can think
Where
of-
for the moment we don't have the constraint of energy.
Yes, but we can imagine when we're talking about collaborative, I don't know if we need to only focus on collaborative editing or collaborative applications in general. Because collaborative application in general does not imply necessarily a person behind a laptop doing a job. Any object can be part of a collaborative application. And this object can have resources constraints. I don't know if we can think of collaboration this way. Do we mean by collaboration always a user using a desk laptop or something with no resources constraints? Or collaboration implies any application that where objects are collaborating? In this case, using Diffie-Hellman would be also problematic.
Yeah, so you have the assumption of the energy consumption, and
Yes.
for the moment we don't have that yet. that, but
We
We
start
could-
having it with the dots.
so,
For example, we start having some dots in our collaborative editing session. For now, we are using a Raspberry, so it still does the trick, but maybe we should take in account resources.
Raspberry is still very strong compared to IoT devices.
I do not know actually. So.
IoT device, like this can always go strong.
Okay. Say so.
I hope.
Yeah, so basically this is why we didn't use DFL, because it exists several versions of distributed.
yeah, I understood that in your context is you eliminated that. But we might think in
Yes.
our context which is better.
And in our context, we don't have GK
Key management service.
because it's a spot. In fact, it's if you launch an attack on the KMS, your system is dead.
And this is why what I told her is that I couldn't just take it the way it is
Yeah.
and apply it to. We need to think.
Yeah, but
about these
yeah,
issues.
but you could think that you can have a distributed management of that.
Yes, this is.
It's a point of extension for that.
Yes, because
Could be.
this area key management server can be actually played by, because all this, they are not all very constrained. In a group, we can have very constrained devices, but others that are a little bit less. They can play the role of area key management server. In this case, we are not in centralized architecture, but we are in much more distributed one. I think it's more interesting than saying we implement DFL1 on all members. Because if we say that, we imply that all the members of our collaborative applications are not constrained, which is not always the case. It can be a good idea to think about these things regarding this protocol.
Can you turn back to the result slide?
Yes.
Maybe the previous one, the one with the numbers.
Okay, the complexity of
Yeah, complexity.
not this one. This one. I'll just give two first.
No, the complexity. So
Ah,
is that
okay.
a chart?
Ah.
I just
Yeah.
Sorry. This one.
So member leaving is the same as the 5, right? So the member leaving complexity is the same as 5 as the
In this case,
But,
the valid. So what about it without validity?
yes, you are wondering about why these values are the same.
No, I mean your protocol and the very add-on. Is that very add-on is
Very
is that the one that we based on?
Yes, yes. It's not exactly. What I said here is that the complexity is less or equal to this one. Why? And here I will go back to this result. It's less, but if at certain moment, which we find out in our experiments that it's around 50%, it becomes more than Virtue and all, we just switch back to this one. Which means that in this case we change the key. We don't bother finding out the members that have the same tickets or not. We say, okay, enough, we change the key for everyone. So we go back to Virtue and all. So this is why in this, here I said that the complexity of our protocol is less, or in the worst case, equal to this complexity. And why these two ones are equal? Because basically Virtue and all, in case of an unexpected leave, they use LKH. This is what we have. But in this case, when the member leaves, it's not an unexpected leave, Actually, there's no rekeying in marks between enroll and our protocol, but in LKH, as it is the event-driven protocol, the rekeying is taking place.
But isn't suppose your is that the battery at all is similar to marks?
No, no.
They don't use AMSA?
For instance, here, which means that in marks, this is an old protocol, they don't take into account the unexpected leaf events. So they say that in our case, we only consider when a node leaves the group at the end of its duration time. But this is considered as an important protocol, state of the art in this